Okay, hello everyone and welcome to this first session of Warwick Data Science Society's and Warwick Math Society's workshop/lecture series on data-driven linear algebra. So to start off, apologies that we last minute changed this workshop from being on Teams to on YouTube. We just found that the quality of the team screen sharing wasn't good enough to clearly see like the whiteboard here. So apologies for that. The engagement isn't quite the same. But still, want to encourage questions. If there's any questions, you want things reiterating, any concerns, please just pop those in the YouTube chat. I'll keep an eye on that. There's a bit of latency, so it might take me a few seconds to get back, but I'll try and keep an eye on that. So in terms of actually going through the session, we're going to break this into two parts. There's no real difference between the first and second part. We're just going to have a short break in the middle, just to give you a bit of time to take everything in and just relax for a second. So the first question that I want to ask is just, can you read what's on this screen all right? If you can't, or if you can't hear me, if there's any issues with that, please pop that in the chat right now. We can get that sorted before we get started. And so also, obviously, because we're streaming to YouTube, there may be some technical issues. I have prayed to the Wi-Fi gods, but being on campus Wi-Fi, no promises there. So if there are any issues, please shout up right away. I can go back and repeat things that were lost if there's any issues. Okay, and also, naturally, the recording of this event will be straight up on YouTube after. If people want the notes that I make, then I can get this sent out as well. Just send the Society a message on Facebook. Okay, so let's start by, I'll just introduce myself, say a bit about my background, my motivation for running this workshop. So I'm Tim. I am the president of Warwick Data Science Society. I am a third year maths stats student in the fourth year of my degree, having done a placement year over the last year. And so even though my degree is in mathematics and statistics, my background is pretty maths heavy. I'm a big fan of algebra and analysis, and so I have very much an appreciation of that more heavy theoretical side of maths. And so some projects that I worked on related to linear algebra, just I guess my qualifications for teaching this, is I'm a developer for this package known as Matrix, which is a linear algebra package in Python that uses multiple dispatch in the same way that MATLAB would. And I've also done some work in portfolio optimization in finance using kind of analytical matrix optimization methods. So in terms of my experience, I've worked at Bet365, done Humvee, which is a data science consultancy firm, and last year I spent at AstraZeneca, the pharmaceutical firm. And so from that, I think I have quite a wide understanding of the different applications of mathematics and statistics. And so this workshop's not going to be overly theoretical. I want to kind of focus on the actual applications and data-driven uses of linear algebra. And so hopefully that helps me in doing so. And so just some examples of the way that I've used linear algebra in the past, just as I guess the motivation for why linear algebra is such an important topic to know, even if you're not a hardcore mathematician. So I did a lot of work last year at AstraZeneca on smoothing of signals. So you might not immediately see how that relates to linear algebra, but it turns out that if you have these complicated signals and you want to try and figure out, I guess, the fundamental signal without the noise, there are linear algebraic techniques you can use to do that. Also lots of work on regression, so fitting lines or curves that best fit some data, or these things called particle filters, which are a technique used to model systems that have kind of an underlying process with then added measurement noise and process noise. And so the actual motivation for this workshop, why I want to teach about linear algebra, is because really linear algebra is an incredibly powerful tool set. And even more importantly, it's a very standardized tool set. And if you can take a problem and reframe it in the language of linear algebra, then suddenly you have this wide range of tools and techniques you can apply to let you solve things. And so actually, knowing those and knowing what sorts of things you can do once you have your problem in a matrix-based form is really important and opens up a lot of applications. An example I want to share that you can have a look at later. I'm just going to pop the link to this in the chat. This is just kind of like a motivating example of why linear algebra is important. It's a blog post I wrote about a coding question that Google use for their interviews. And the normal approach to this, the computer scientific approach, is using either dynamic programming or kind of some variants of that, quite heavy computer science techniques. But it turns out you can actually represent this problem as a linear algebra problem, just as some matrices. And then you have access to this whole suite of linear algebra tools that we learn at university and kind of in courses like this. And it actually becomes a really simple to solve problem. I think I solved it in about 7 lines of code compared to the normal dozens of lines. And so that's just one example of how if we use linear algebra, we can really solve some interesting things in simple ways. Okay, so about this actual workshop. So this is split up into 3 parts, taught on Monday, Wednesday, and Friday. So I have on my screen here what the content is for the 3 parts. So today we're in session 1, and that's going to be about the theory. It's not going to be overly theoretical. It's more kind of setting up our motivations and kind of what our aims are in using data-centric linear algebra. And then we'll focus on actually kind of the practical application on Wednesday, how we can actually by hand compute some of these things we're talking about. And then on Friday, we'll look at the application of these using coding. So we'll use a bit of Python, but we'll also get translations in other languages to actually see how we can apply these to some real problems. And you may have seen on WDSS's Facebook an example of using these techniques to compress the image of a cat. We'll look at examples like that. And so we'll return to talking about exactly what we're going to be doing in session 2 and 3 when we get to those sessions. But today we have 5 things to look at. So first, some preliminaries, just getting everyone up to the same standard. We're expecting very little prior knowledge for the session, so we're going to just work through a few things. We're then going to look at these things called decompositions and kind of explain what a decomposition is, and then learn about this specific decomposition called the singular value decomposition. And that's really the prime focus for this entire workshop series. This thing called the singular value decomposition, it's a really important tool in a wide variety of fields. I'm going to learn what it is and how to use it in practical examples. We're then going to look at this thing called low rank approximations. That will make more sense when we get to that. And finally, a geometric interpretation of what the singular value decomposition means. And so a few notes on the style of this workshop series. I'm going to be presenting in a similar way to how a normal lecture would be taught, but hopefully being a bit more open to questions. So if there are any questions, please do ask up. It's very important to catch any issues early than trying to, so rather than just trying to kind of go along if you're not following completely. I try to kind of improvise when I'm teaching a bit more. I think just copying out from notes is a bit boring and unengaging. But the side effect of that is that I will make mistakes. So if you do spot anything that looks a bit strange, either point it out or just say, can you explain that thing again? And I might spot it for myself. And so we are going to go through this content fairly quickly because we want to discuss this whole topic and its applications in 3 workshops. So I wouldn't worry too much about taking notes. That's not really the idea of this. You can come back later and review it. This will always be up on YouTube. But you might want to jot down some key ideas. If there's something you haven't seen before, especially definitions, then it might be a good idea to just put them down on some paper somewhere so you can refer back to them if you need it. But yeah, you can come back to the recording at any point. So really just sit back and try and take it in. And so yeah, prerequisites, there really are none. If you have an A-level understanding of matrix algebra, that's wonderful. The important thing to bear in mind though is that each session depends on the last. So to do session 2 and 3, you will need to have watched the previous ones. And also, we'll be doing a bit of coding in session 3, but there's going to be no prerequisites for that. I'll make the code as clear as possible, so you should be able to follow along even without knowing how to code. That will be in Python, but we'll get translations in MATLAB, Julia, and R sorted. Those will go up on the Facebook event page at some time fairly soon. Okay, so the actual motivation for learning about data-centric linear algebra, and specifically about this thing called the singular value decomposition. So this may be a controversial statement, but I actually think many statisticians and mathematicians will agree, is that the singular value decomposition is the most important technique or tool in applied linear algebra. It appears absolutely everywhere, and more importantly, if you want to make money using linear algebra, the singular value decomposition is probably the best way to do that. because it's used in a wide variety of fields, in statistics, in signal processing, machine learning, it's critical, optimization problems, managing portfolios in finance. There really is a massive variety of things it's used for. And it's also useful in theoretical maths. You can use it as a more elegant way of solving problems that would otherwise be a bit tedious. And so you may be wondering, okay, this sounds very important. Why haven't I heard of it? If it's so important, why isn't it in my first year algebra course or something like that? And the reason is, it just takes time for universities to update their syllabus and change to a new world, because the singular value decomposition is very powerful for data-centric applications. And often when you want to apply it in practice, you'll need a computer to actually calculate the values. But that's not a problem now. We have fast computers and we have lots of data. And so the singular value decomposition is becoming more and more important with time. Actually, MIT in their linear algebra course, their introductory one, they recently updated it, I think a year or two ago, to include the singular value decomposition in the beginner's course. So it is starting to take hold of the academic scene. And so at a very high level, what is the singular value decomposition? We'll define it properly in this session, but just as some kind of motivation before we get there, it's essentially a tool for reducing the dimension of our data. You can imagine we're working with some really complicated data in really high dimensions. Each bit of our data is a million dimension vector. That's too much for a human to work with. And so the idea of the singular value decomposition is to reduce that into fewer dimensions, taking the most important features of our data to have this really dense representation that actually has a lot of intuitive understanding, kind of getting rid of the noise and unimportant bits of the data. Okay, so that's all kind of the setup. It's also worth mentioning that there are a few things we're not going to cover just in the name of time. There's this thing called the randomized SVD, and that is an algorithm kind of based on these ideas of randomized linear algebra. It's a fairly new field, and it's a really clever idea. Have a search for it after these 3 workshops if you're interested. We're not going to deal with issues of alignment. Again, just Google it if you want to know more. Kind of robust estimates, so the robust principal component analysis. We'll talk about the principal component analysis in session 3. There's a robust version which works for missing data. That's kind of the backbone of Netflix's recommendation system. We're not going to explain how that works, but again, you can search up for it. Also, when we actually do the singular value decomposition, we're going to use a very inefficient algorithm. It's a simple algorithm, that's why we're going to teach it, but it's not the most efficient way of doing things. So we're not going to get into the details of efficient ways of computing it. For that, we'll just get Python or MATLAB or whatever to do it. We won't understand the algorithms they're using, but hell, they're fast, so we don't care. Okay, so we're going to start off with some preliminaries, and specifically some definitions. And so if you're very familiar with an algebra, you might be looking at this and going, okay, this is a waste of time. I know what a vector is. I know what a matrix is. But what I want to try and introduce to you is different ways of thinking about these concepts that you might know already. And specifically, geometric, algebraic, and data-centric interpretations of these ideas you might know already. So we're going to start with a vector. So a vector is basically a column or, I guess, a row of numbers. And so we might write it something like this. So we have a vector v, and it contains values v1, v2, all the way down to vn. And we also might represent this as a row vector, in which case we would use the little t symbol, meaning transpose. And that would look something like this. Okay, so that is our vector. Well, what does that mean? What is a vector? Well, let's start with the geometric intuition of a vector. And I'm also going to mention, throughout this entire session, we're going to be sticking to real numbers. So no complex numbers, no kind of integer fields or anything complicated. We're living in the world of normal decimal numbers. So what a vector is, essentially, it is a point in an n-dimensional space. So each of these points here in the vector, those give you one coordinate out of n dimensions. So you can imagine in the case we had a vector like 1, 2, and 3. We're in a 3-dimensional space. Let's have a go at drawing that. Something like this with our coordinates x, y, and z. And then this vector has x coordinate 1, y coordinate 2. Wait, so y coordinate 2. I've done these in the wrong order here. So y coordinate of 2, and then z coordinate of 3. So at some point up there. So that's all a vector is. So algebraically, we would consider a vector to be an element of this thing called a vector space. Now this is very technical. We're not going to get into exactly what this means, but it just shows that, you know, there are different ways of thinking about these concepts. And a vector space, yeah, we're not going to mention what that is. It's basically a thing. There's these 8 key kind of axioms, or we'd call those, I guess, rules in quotes there, not the technical name for them. And vectors are things that basically obey these rules. And so in a data-centric view, what is a vector? Well, it is data. Essentially, you can think of a vector as either an observation or a predictor, or kind of a response variable, like something you're measuring. So we could imagine here that this V transpose, all this is, it's all the data about a certain person. It's like one row of our data set. And each of these V's gives some kind of measurable property about that observation. And in a similar way, a column vector like this might represent, for different people, all the values of one measurable property. So that's one way of thinking about a vector. So let's next talk about this thing called a dot product. So we would denote this either with a dot, or sometimes we might write it like U transpose V, or something like this. This is known as the inner product notation. So this is a thing called a dot product. You might have come across it before in A-level maths, but we'll define it here. So let's start with the algebraic definition of it, because this is the actual kind of how we would compute it. If we have U dotted with V, all that means is we take each element of this vector U and each element of this vector V, and we multiply those together. And so we do this from I is 1 up to n. So we just kind of take these two vectors side by side and times them across, then add up all of those products. And another way of thinking about this is as when we do U transpose V, is thinking of these vectors kind of as matrices. We'll explain what a matrix is in a second, but you know, this U transpose is something long and thin like this, and then this V1 is something tall and thin. And we can think of this as just like a matrix product between these different terms here. So that's another way of thinking about that. But geometrically, what is a dot product? Well, one way of thinking about it is that it's got something to do with the angle between any 2 points. So it's the angle between two vectors, say. And it's a bit more specific than that. You have to normalize these vectors first, so they have a length of 1. But essentially, a dot product is talking about what is the angle between these 2 points, or these 2 vectors. And there's not really a data-centric interpretation of a dot product. So we next have a matrix. Well, a matrix is just some entries here. Let's call them A1, and it's going to be an M by N matrix. This is going to go up to A1 N, all the way down to AM1, and all the way down here to M and N. So it's basically just a grid of numbers. And how can we think about this geometrically? Well, this is kind of a linear transformation. And so what do we mean by a linear transformation? Well, basically take some sort of space, say 3 dimensions, and do something to it. And when we say linear, what we mean is, well, there's 2 ways of thinking about it. One is that parallel lines stay parallel. Another one is that lines through the origin get transformed into lines through the origin. So that's one way of thinking about it. Rotations, reflections, scaling, stretching, skewing, those are all linear transformations. Algebraically, we think of this as a linear map. Not going to explain exactly what that means. That's not really the focus of this course, but that's one way we could think about it. And in a data-centric sense, and this might be a bit of a new idea to people, but it's a very nice way of looking at a matrix, is as a data set. If I have a matrix A, I can think of it as either a collection of row vectors or a collection of column vectors. So for example, I could think of A as multiple, so this is an m by n, so it's going to be m of these, multiple row vectors. And we're going to transpose those because they're row vectors like we saw up there. Okay, so that's one way we can think about a matrix, as these row vectors. Or another way, we'll be thinking of things as column vectors. So going up to n now, because there's n columns, and thinking of them as these different columns here. And so that's a very nice way of thinking about matrices. Rather than their actual individual elements, we think of them either as collections of observations, these rows here, or collections of predictors, things we can measure. Okay, so two more things we're going to talk about, then we'll actually get on to talking a bit more about the bulk of this course, the single value decomposition. What is the rank of a matrix? And we would denote this simply as rank of a matrix A. So let's start with the geometric definition of this. So geometrically, what the rank of a matrix kind of represents is if we took a unit sphere, so imagine we're in 3 dimensions, we'll take the sphere in 3 dimensions, and then we're going to transform that through the matrix, and that might get turned into maybe an ellipsoid, or it might get flattened down into an ellipse, or maybe even just a line or a point. And the rank corresponds to what dimension this resulting sphere is going to be after we transform it. So it's the dimension of a transformed sphere. And we'll come back to this right at the end of the session when we talk about the geometric interpretation of the singular value decomposition. A way we can think about it in terms of algebra is that it's the number of linearly independent columns, or rows in fact, linearly dependent columns or rows in the matrix. And when we say linearly independent, what we mean by that is that there's no combination of those columns or rows that give us the zero vector. We can't add them up to make 0. But those definitions are quite heavy. The data-centric definition is actually quite a nice one, and it comes down to how many non-redundant observations or predictors we have. It means the same whether we look at predictors or observations. So for example, imagine we had a data set like this, where we had the values 1, 0, 0, 0, 1, 0, and 1, 1, 0. And these are kind of different measurements. So this is measurement 1, measurement 2, and measurement 3. Well, in this case, measurement 3 is redundant, because if I know measurement 1 and measurement 2, I can just add those together, and that gives me measurement 3. And so in a way, we can think of M3 as being a redundant predictor there. And so the rank of a matrix is basically how much we can compress this data, like what is the lowest representation we can have, so that none of the predictors or observations can be given as combinations of the other ones. And then the final thing we're going to look at is what it means for a matrix to be orthogonal. There's no real notation for this. We just write, a matrix is orthogonal. And so let's start with the algebraic definition. So a matrix is orthogonal if and only if when we take its transpose times by itself, or we take itself times by its transpose, we get the identity matrix. A matrix with just ones down the diagonal, zeros everywhere else. It's worth noting, let's do this in green, that A must be square for this to happen. It's impossible to have both of these being true if A is not a square matrix. You can have one of them being true, in which case we'd say it's semi or pseudo orthogonal. But that is a heavy definition. It's not intuitive at all. Let's focus on the geometric one. And that is an orthogonal matrix is either a rotation or a reflection. So when we're talking about these linear transformations, they take our space and transform it in some way. Specifically the ones that are rotations or reflections, those are our orthogonal ones. And so finally, the data-centric view of this is that, I'm going to put this in quotes because it's a bit kind of a bit fluffy. A matrix being orthogonal or kind of a data set being orthogonal, because matrices and data sets, we saw that equivalence above. It basically corresponds to there being no correlation after we kind of center our data. If you're not that familiar with statistics, that's not very helpful, but if you are and want to kind of try to understand what exactly that means, we'll think about the definition of correlation. You'll know that the numerator has this term in it. And if our data is centered, then these are going to be 0. So then we're left with the sum of xi, yi. And if you remember back to above, that corresponded to the dot product here. And so if something's orthogonal, then they're essentially uncorrelated after we centered them. But this definition here of reflection and rotation, that makes the most sense. So let's just give an example of what kind of a data-centric view of a matrix might look like. So let's imagine we have these images here, and they're going to be of people's faces. So we have someone smiling here, we have someone frowning here, and someone with a very long-shaped head here. And so we want to represent these as a matrix. Well, the first thing we're going to have to do is to, well, actually, yes. So let's draw our matrix out here. And if we remember from this kind of above view here, that each of these kind of rows of our matrix are kind of observations. They are individual units that we can measure. And so what we're going to want to do, we're going to want to take our observations here and put those as the rows of our data set. And so to do that, we're going to have to take these images and flatten them down. So we can imagine we turn these, let's do a proper square here. We turn these kind of long images, square images here, into these really long and narrow kind of series of pixels. And then those become the rows of our data sets here. And then each of the columns, these correspond to one of the pixels in our image and the value that that pixel takes over the different images. That's kind of one way of looking at a matrix like that. Okay, so we're now going to have a look at kind of a helpful idea that's going to come in useful when we're thinking about this thing called the singular value decomposition. And it's going to center around a new way of thinking about matrix multiplication. So you might be familiar with matrix multiplication. Hopefully you are. So let's say I have matrices here. We have 1, 2, 3, 4, 5, 6. And matrices 1, 2, 3, 4. And these have dimensions 3 by 2, 2 by 2. These inner dimensions match, so we're all good. We can take the product. And these outer ones are going to give us the size of the resulting matrix. So here we're going to get a matrix that is 3 by 2. And we do the multiplication by kind of going across the rows and across the columns and kind of timesing those together. So 1 by 1 is 1, added to 2 by 3 is 6. So we get 7 there. We have 1 by 2, 2 by 4, that's 2 and 8, which is 10. And then we can carry on like that. We'd get 15, 22, 23, and 34. So that's how we would do matrix multiplication like that. It's a bit of a faff, and there's no real intuition as to what's going on there. So I want to think about a different way of doing matrix multiplication. Let's imagine we have matrices A and B. And these are m by n and n by p matrices. And we want to calculate what the matrix AB, which is an m by p matrix is. Okay, well, let's think about what the ijth element of this matrix is going to be. So when we were looking above, we kind of went, if we wanted the ith row and jth column, so here it's I is 2 and j is 1, we went across the ith row and down the jth column in the second one. So representing this as a sum, we have something like this. So we had the ith column of, actually, let's not write it as a sum just yet. So we had something like A, and then we took the ith row, the first column, and the first row and the jth column of B. And then we kept adding these together, so 2, the second one, and we keep carrying that on all over that common axis, which has n things in it. So then we have n and j like that. And we can represent this as a sum. So this is the sum of a ik, b, kj, going from k is 1 up to n. And so now we're going to pause for a second and go back to thinking about matrices using this sort of data-driven approach. And we're going to write A like this. We're going to write A as a matrix of rows. So we're going to have A, 1 transpose, A, 2 transpose, all the way down to, well, there was M rows, so AM transpose. And each of these have n elements in them. And we're going to write B as a matrix of column vectors. So we're going to have B1, B2, all the way up to BP, because B had P columns. So these are all column vectors here. Well, now let's look at this here. We're going through all the elements of A, kind of for a fixed I and for a fixed J, and all the elements of B, and timesing them all together. Well, that looks an awful lot like the dot product that we had before. In fact, it is the dot product that we had earlier. And so we can think of this matrix multiplication as the dot product between AI and BJ. And so really all a matrix all matrix multiplication is giving you a matrix of dot products. And so we could write AB as something like this. So A1 dot B1, then we're going to have A1 dot BP, then AM dot B1, all the way to, let's add these dots in, to AM BP. So another way of thinking of matrix multiplication is as building this matrix of dot products. And when we start to think about what a dot product means geometrically, either as these angles or as another way of thinking of those is projections, this starts to take on some kind of very interesting meaning, as it's the matrix of the angles between these observations and these kind of you can think of these as predictors or ways of mixing those observations together, and it starts to take on quite an interesting meaning. And so I'm also going to give another result, and I don't have time to prove it, but if you think about it for a bit, it should kind of make sense what's happening. So first we're going to have to define this thing called an outer product. And so when we talk about the dot product up here, another word for a dot product is an inner product. And its outer product is kind of the opposite. And if we have vectors u and v, let's say u is u1 all the way down to un, and v is v1 down to vn, then what the outer product of these two vectors is, denoted by this cross symbol with a circle. We could also write that as u v transpose. Now don't confuse this with the u transpose v we had before. These are opposite ideas. This is a u v transpose. It's going to be, well, u is this kind of long vector here, and v is this kind of v transpose is this kind of wide vector going across here. And so this is going to give us as a matrix that looks something like this. So we're going to have the first term, we're going to take the first element of u, so u1 times by v1. Then for this one, it's going to be u2 times v1 again, because it's still in this column here. Then we carry that down to un v1. And then we can go across, and we'll end up with still u1, but now vn, u2 vn, all the way down to un vn. So whereas an inner product kind of took us down to a single value, this blows us up into a whole matrix of every possible combination of those two elements. And so this leads us to a result, which is another way of thinking about a matrix product. And And so this is actually going to be the representation of B times A. Actually, no, that doesn't make any sense because the dimensions don't match up. Let's define two new matrices. So C is going to actually be columns now. So C1, C2, all the way to C. We're going to need to have the same number for these. Let's call it Cn. And then D is going to be something like row vectors now. So before we had columns, then rows. Now we're going to have rows and then, sorry, columns and then rows. So we have something like this. And then another way of representing CD is as a combination of these outer products. So we can actually write the product CD as the outer product between C1 and D1, all the way up to the outer product between Cn. Sorry, that's the wrong way around. Between Cn and Dn. And so writing that in this kind of this vector form, it's C1 D1 transpose all the way up to Cn Dn transpose. So that might seem a bit heavy, and I encourage people who are kind of into their mathematics to try and prove why that is the case. You can actually take it straight from this sort of sum above, but just view it in a different axis. Think about why that is true. But essentially what we're saying here is that we can write CD as a combination of these products of kind of single vectors, single column vectors and single row vectors. And it's quite a beautiful idea. And then we can go one step further, and that is, what if we want to compute C, and what am I going to call this? I guess let's call it E, D, where E is a diagonal matrix. So something like this, and it has elements E1, E2, all the way down to En, and then everything else is zeros. If we're computing something like that, actually, it has a very similar representation to this, one above. All we have to do is weight these by those diagonalized elements. Let's do this will be E3, and then ... all the way up to En, and then this one here. And so this is going to come really handy when we start talking about the singular value decomposition, because we can basically take any matrix multiplication, or kind of a triple matrix multiplication with a diagonal in the middle, and think of it as a sum of these kind of low-level representations. And more importantly, each of these matrices, the products we get from here, these are going to have a rank of 1. And the reason is that, what we're kind of doing here, we're taking a single column, and then we're multiplying it by each of these values here. And so thinking about the data-centric interpretation of being of rank, oh, let's not delete that. When we're talking about how redundant is our data, we can see here that our data is just kind of duplications. Where have we gone? It's just duplications of this same vector being repeated again and again. So this has as a rank 1. So we can write this matrix as a combination of rank 1 matrices. Okay, so maybe some kind of heavy preliminaries now. We're now going to get into the actual kind of bulk of today's session, which should be a bit lighter than this introduction. But hopefully it was interesting to see these kind of data-centric views on how we can do linear algebra. So we're now going to talk about these things called decompositions. Decompositions. So what is a matrix decomposition? Oh, that's not a straight line. There we go. Okay. So a matrix decomposition is kind of the matrix generalization of factorization. So imagine we had some polynomial x squared minus x minus 6. Well, we can write that as x minus 3 and then x plus 2. And so this is essentially they mean the same thing, but this representation on the right is much more useful because it's going to tell us, for example, where the roots of the polynomial is. We know that this polynomial is 0 when x is 3 or when x is minus 2. So basically, all a decomposition is, this is a very loose definition. So a decomposition is a factorization of a matrix into products. So basically, we take a matrix and we write it as a product of other matrices, and hopefully these products will come with some interesting properties that will help us do more interesting things. So an example of a decomposition that you might have seen before is the eigen decomposition. This is also known as the spectral decomposition, or simply as diagonalizing a matrix. And so this comes down to writing a matrix A as some matrix P times a diagonal matrix times the inverse of that matrix P. So here this is diagonal, and P is invertible. Obviously has to be, or we couldn't invert it. And so this is a very useful definition. Why is it useful? Well, if I want to take a to the power of 100, well, I can write this as p d p inverse to the power of 100. And then I can write this out as p d p inverse, p d p inverse. Keep repeating this 100 times, p d p inverse. And then all of these p inverses p's will cancel out, leaving us with just p d to the 100 p inverse. And calculating the power of a diagonal matrix is very easy. You just take the powers of the diagonal itself. So this is a very useful property that we can get by having our matrix represented in this format. Okay, but just pressing the wrong button there. Okay. So what are the problems with that though? Okay. Well, the biggest problem, it doesn't always exist. So this this decomposition here, A into PD, P inverse, doesn't always exist. In fact, it only makes sense for square matrices. So these two factors are very limiting. And even more annoyingly, the actual check to see whether it does exist is just as complicated as actually computing it. And so if we had a really massive matrix and we tried to compute it and then figured out that actually there isn't a solution, it would take us just as long to do that as it would to actually compute it in the first place if it did exist. And so essentially we're wasting a lot of time in doing that. So what we would really like is a more flexible and general decomposition that works for all matrices. Yeah, just that. We want a decomposition that works for every single matrix. And so we want to step beyond the eigendecomposition that we might have seen before into this thing called the singular value decomposition. And we, well, let's write that in full. So singular value decomposition, or the SVD. So I'm noticing, looking at the time now, that we probably are going to overrun a bit. So apologies for that. We're going to get to the singular value decomposition and then take a short break. And hopefully we'll only be about maybe 15 minutes overrunning. But obviously the recording will be up later if you want to watch the end of it, if you have to go. So for the singular value decomposition, we're going to have a matrix X. And so annoyingly, we're going to represent X using columns of our observations. So we can write X as x1, x2, all the way up to xn, where we have n observations. And each of these are our columns. Each of these are our observations. So you imagine in the image case we saw before, this is one person's face. This is another person's face. And so this is a bit frustrating. We saw before that actually we would like to represent these as the rows. But it turns out that all of the theory for the singular value decomposition works best when our observations are column-wise. And so to avoid confusing you when you go and look at other resources on the SVD, I've decided to stick with the convention but I do encourage you to have a think about how things would change if we had them row-wise. And I'll point out a few things as we go to kind of explain what changes might be made. And this X here, it's going to be a P by N matrix, where P is the number of predictors, so the number of pixels in the image in this case, and N is the number of images that we have available. And so each of these xi's is in the real numbers, a p-dimensional space in that. And we're assuming here that P is way bigger than N. We have a lot more kind of pixels than we do images, which is, in most cases that we use this singular value decomposition, is a reasonable assumption. Okay, and so the singular value decomposition says that we can write X in this format. So U sigma V transpose. And so what do these matrices look like? Well, U is going to be, okay, so I see my screen is frozen for a second, so we'll just give it a second to reconnect, or you won't see what changes I'm making. So yeah, so we're going to write it as this U sigma and V transpose. And these are going to have really kind of tangible real-world interpretations. So these are not kind of generic matrices. These actually represent something about our data, and we can use that for understanding more about what our data is doing. So I think everything's unfrozen now. There we go. So U is going to have these columns here, U1 up to UP. And what each of these represent is kind of, I guess, what we'll call an eigenface. Okay, seemed to lost complete connection to my screen. Let's just try reconnecting that. Okay, we should have the screen back again. Sorry about that. Okay, so these are our eigenfaces. And so each of these look like a face. But they're, the idea of these is that these each represent kind of the most important aspects of what makes a face. So these are arranged hierarchically. I assume everything's coming through again okay now. It would be great if someone could let me know in the chat. And so these are kind of arranged hierarchically in order of importance. So you can think of this as like a new basis for our faces, kind of a palette that can be used to compose all of these faces. And U1 essentially is the most important aspect of what it means to be a face. And then U2 is a bit less important, U3 is a bit less important. And then we can add all these together to make up a face. And the important thing, those are ordered. And the importances of these different values are represented by the values in this sigma matrix. And so sigma is a diagonal matrix looking something like this, going up to P, with then just zeros padding the bottom here, and the rest are zeros here. So it's diagonal, but it's a rectangular matrix just padded by zeros at the bottom there. Okay, and so these different sigmas, these give the importances, well, the corresponding importances for these vectors u1 up to up. Okay, and then finally we have this vector v transpose, which I'm going to write by transposing the insides rather than the outside, which is going to look something like this. So v1 transpose all the way up to vn transpose. So let's just point out this is a p by p matrix, this is p by n, and this one is n by n. And this has maybe a bit harder of kind of an interpretation behind it. But what this kind of means is that each of these columns here is kind of crossing across the rows. What these represent is the mixtures of U1 to UP needed to reconstruct x. Well, in this case, it's x1, and the next one would be for x2, x3, etc. So these is kind of a palette in order of importance, and these columns here that kind of cut across these v rows determine how we combine this palette together to reconstruct our initial thing. And then we also have these rows across here. And so what one of these rows represent, these are essentially how kind of the mixtures change. So I guess, yeah, so they're essentially kind of like a time series. I'm going to put this in quotes again. For how the contribution of one eigenface changes over observations. So this one in the middle here, this corresponds to some eigenface in the middle of this U matrix here. And it shows how for every single matrix, every single face in our original data, how the contribution of that changes as we work through the data set. So that's kind of the intuition of what this representation means. And there's a few conditions that we put on these. So U and V are orthogonal. And so what we mean by that is that U transpose U is U transpose is U transpose is the identity, and then the same for V. Or in other words, the geometric interpretation, these are rotations. And then for sigma, we have the assumptions that these sigmas are decreasing in value all the way down to sigma p, which is greater than or equal to 0. So summing this all up, the way that we view this singular value decomposition is that we break up our image into these different kind of components ordered by their importance. The importances are given by these sigmas, and then this V matrix tells us how to take these eigenfaces and combine them together to reconstruct the original. So that's what the singular value decomposition is. These are known as our singular values. These are known as our left singular vectors, and these are known as our right singular vectors. So with that, we're just going to pause for a minute or two just to have a quick break. If you have any questions, pop them in the chat now. Otherwise, after that, we'll go on to the properties of the SVD, how we can represent this as the sum of low-rank matrices, and then the geometric interpretation of the SVD. So I'll join back again in a minute or two. Okay, welcome back. So we're now going to have a look at the properties of the SVD. Just a few high-level properties. So the first one is that the SVD, well, actually, let's start with the most important one. It exists. So for any single matrix, the SVD exists. And this is a really powerful property that we didn't have with the eigen decomposition. And actually, many decompositions do not have guarantees of existence. We'll show that it exists by actually deriving the SVD and computing it in the second session. So that's nice. And secondly, it is unique up to sign. So given these conditions that U are orthogonal, so U and V are orthogonal, and that these sigmas are decreasing, the matrix is unique. Apart from, let's say, if we took U2 and V2 and negated both of those, then we'd also get another SVD that was equally as valid. So apart from changing the signs of those, we have a unique decomposition. So that's a very useful property. What else do we have? So if the matrix X is real, then U and V will also be real as well. So again, that's nice. We can stick in the world of real numbers, but if X is a complex matrix, then no guarantees on U and V. Okay, what else do we have? So I guess we can have, so these sigmas are allowed to be 0, and they can become 0 at any point. Say maybe from sigma 4 onwards, they're all 0. Well then, so the number of sigmas that are not 0, that is the same thing as the rank of the matrix X. And we'll actually see why this is in a moment. So that's a nice property. Okay, yeah, there's one more property that I won't mention here. I might get time at the end just to add it. Okay, so now the most kind of important thing is that, so we look at this matrix here. We have a matrix of columns. We have a matrix of rows here, and a diagonal matrix in the middle. So this brings us back to this result that we showed before. You can represent a matrix with a diagonal in the middle when we have them as columns and rows, as this sum here of these rank 1 matrices, these rank 1 outer products. And so what this actually shows is that we can take the matrix X and write it in the following format. So X is sigma 1. It's going to be U1 V1 transpose plus sigma 2 U2 V2 transpose all the way up to sigma P of that doesn't seem right. No, it's going to be up to sigma n, because we'll reach the zeros first. Sigma n of un vn transpose. And I think that makes me realize, I think that there's a mistake in my matrix. Yeah, this should be an n here. Because it's a p by n matrix, so there can only be n diagonals going across. And p is much bigger, which is why we had the zeros at the bottom there. So we can write X like this, and just a reminder, U1 is a column, and V1 transpose is a row here, and that's going to give us a matrix here which has rank of 1. So basically, it's just going to be, I guess, yeah, this is the point I was making earlier, that these ones across here, these V's, are the combinations of each U1 of each of these components over time. Or over each observation. So we're just taking different amounts of these over time, different amounts of our palette over time. That goes all the way on to sigma n, un, vn transpose. Okay, so why do we care? Like, what's the important part of this? Well, the important part is that these sigmas are decreasing. And so you can think of this as, we decompose this into these rank 1 matrices. But the contribution of each of these matrices gets less and less as we go through. So this sigma 1 is probably pretty big, showing that this first combination contributes a lot to the matrix. This next sigma 2 probably still pretty big. By the time we're at sigma n, this is adding nothing. This is a really tiny contribution to a matrix. It might even be 0. And so the idea is, at a certain point, we're going to call this R, we're going to cut things off and just stop it. We're going to truncate it. And that's going to leave us with an approximation of X, which is going to be U, we're going to put a hat on it, sorry, not a hat, a tilde for approximation of rank R, sigma approximated rank R, and then V transpose approximated with a rank R. And so these matrices are going to have sizes n by R by R, and R by P. As we've taken this massive matrix X and we've collapsed it down into only kind of a few underlying outer products that represent the whole matrix. And so that's kind of a really important idea. And actually, this has a sense of optimality as well. So there's this thing known as the Eckert-Young theorem. I believe there was a third person involved, but I forgot the name of that, so apologies to that person. And that was proved in 1936, so still fairly recent maths. And that says that that this approximation, I guess, yeah. So what the Eckert-Young theorem says is that let's consider all possible approximations of the matrix X. So all kind of possible matrices in the space of P by n matrices, and consider all of those that have a rank of rank R. Well then, which of these minimize the difference between the actual matrix X and this rank R approximation in the Frobenius norm? I'll define the Frobenius norm in a second. So kind of what minimizes the distance between these two matrices? It turns out that this minimizing matrix is this matrix here. And so in other words, when we take this and truncate at R, that is the best possible truncation we could do. So if we wanted to represent our matrix using only kind of a certain amount of compression, a certain amount of kind of low-level representation, singular value decomposition will give us the best possible way of doing that, the most efficient way of doing that. And that's in the Frobenius norm. Let's just define what the Frobenius norm is. Let's say we have a matrix A, and then the Frobenius norm is the square root of each of the entries of this matrix squared. And so another way of thinking about that is take the matrix, flatten it out into a single vector, and then consider the length of that vector. And so this x minus x tilde in the Frobenius norm is essentially, if you flatten both those matrices out into vectors, what is the normal Euclidean distance between those two vectors? And so that's the Eckert-Young theorem, and that kind of is what gives the singular value decomposition all of its power. Okay, so now let's consider, well, when should we truncate this R? Like, when's the correct point to cut that off? And so to answer this question, what we can do is we can draw a graph. And usually we would do this using a computer, but for now we're just going to imagine we've done this already. And we're going to plot different R's against the logarithm of these sigmas here. And what we hope to obtain is something that looks a bit like this, say. Okay? So we know that these are decreasing, and we want to pick a certain R at which to truncate. And we can do that by looking for what we call an elbow. And this is kind of a place in the curve where it starts to flatten out a bit. So this would be a good place to truncate, because after this point, every added bit of data, every added kind of bit of rank to the data, the amount of complexity to the data, it doesn't add as much explanation to the actual matrix. So basically we can get a pretty good approximation by stopping here. Another way of looking at this would be to draw this other graph here. So again, we're going to go along R, and then we're now going to look at the sum of all sigma i's going up to R. And this will look something like this, kind of tailing out. And then what we can do, we can pick a certain point here, say 99% of all of the sigmas, cut across, and that's going to give us the R. And so this way we can represent 99% of the information in the matrix using only a certain number of these low rank matrices, or with a matrix with this low rank R here. And we'll actually look in the second session of a formalization of this called the Gavish-Donico method, which was derived in I think 2014, which actually gives us an algorithm which is proved to be optimal under certain conditions for where to find this R cutoff. But for now, we can plot something like that. And so to close off in the last 10 minutes, I'm going to talk about the geometric interpretation of the singular value decomposition. So the geometric interpretation. What does this singular value decomposition actually tell us geometrically about our matrix? Okay, so we have our matrix X, and it looks something like this. So this was a P by N matrix. If you remember, where each column is an observation and each row is one of our predictors. So we can multiply this in two ways. We could take an n by 1 vector, let's call this V, and times that on the right, or we could take kind of a row vector, a 1 by P vector, we'll call this U, and times that on the left. And so the singular value decomposition tells us something about geometrically how these operations take place. So let's start with this right multiplication here. So imagine we have a vector V in an Rn, and specifically we're going to take V to be somewhere on the unit sphere in the space of Rn. So imagine we have, okay, I'm going to try and draw a sphere. It's going to look something like this. That's not terrible. There's the origin, and then V is some vector on that unit sphere. And then we're going to take that, and by multiplying it by x, we're going to transform it into a new space. And this is now going to be xv is going to be in the space r to the p, because n by n, and then we have p by 1 gives us a p by 1 vector. And then so we take this unit sphere here, and when we transform it with x, we're going to end up with an ellipsoid. So this is my attempt at drawing an ellipsoid. And then the singular value decomposition, I guess put one across there as well, gives us information about what this ellipsoid looks like. And so an ellipsoid is defined by its principal axes. So it's one axis here, so the next one's probably somewhere here, and then one going up here. And the lengths of these axes are given by our singular values in decreasing order. 3, and then it would carry on like that. So here we're in 3 dimensions, but P would probably be a million dimensions, and we have some million dimensional hypersphere. And so that's what the singular values could give us. And then these directions here, these are the vectors u1, u2, and u3. So essentially u and sigma tell us how this unit sphere gets mapped by x into this new space. And so I think my screen has frozen again, so we'll just give it a bit of time to catch up. There we go. Okay. And then what the matrix V is going to tell us is what happens when we do the reverse. Let's take U in the space RP. So again, just some U here in this unit sphere in RP. And then we map this backwards using U pre-multiplied with X. And that's going to give us another ellipse like this. And this is going to have this is going to have principal axes here. And these are still going to have magnitudes given by these sigmas. But now their directions are represented by V1, V2, and V3, etc. So that's kind of the geometric intuition of what the singular value decomposition is doing. It's telling us when we're mapping forwards and backwards, mapping these spheres, how do we rotate things and how do we stretch them? And so we're coming close to wrapping up now, but the final point I want to leave you with is that we've represented X, which was any matrix, remember, that the singular value decomposition exists for any matrix, as U, sigma, and V transpose. These are orthogonal, and this matrix sigma is diagonal. In other words, geometrically, U and V are rotations or reflections, and sigma is a scaling. You might want to think for a moment why that is the case, but if we times by a diagonal matrix, all we do is stretch out our space. We don't rotate, skew, or anything like that. No, sorry, we might skew if you scale by different amounts in different dimensions. And so what the singular value decomposition tells us in a geometric sense is that any matrix can be represented, any transformation can be represented as a rotation onto the right axis, then a scaling along the kind of the principal axes of our dimension, so along the actual x, y, z axes or whatever, and then one more rotation to get things back in line. So every single transformation can be represented in that form, and that's a pretty beautiful idea. Although we're not here just for the mathematical beauty, and so that's where the next two sessions come in. So in session 2, we'll talk about how to actually compute the singular value decomposition, and kind of a bit more about what that actually tells us about the data, and then how we can optimally truncate things. And then the third session, which is the really exciting bit, we're going to actually be coding things up for the purposes of, we go back to the start here, 3 different main things to look at. So compressing images, how we can do linear regression, how we can reduce the dimension of our data, and some wider uses, some examples of how the Netflix algorithm, how Google search, and how facial recognition use the singular value decomposition. And finally, we'll talk about the limits of it and other techniques we might want to use when the singular value decomposition just doesn't quite cut it. So with that, thank you everyone for attending this first session. I appreciate there having some fairly heavy bits in it. Feel free to come back and watch it again to take things in a bit more. But hopefully with the next 2 sessions, focusing more on the practice of it and the application, you'll start to see how this all comes together, and it's really a very useful and practical tool. So I'll see you then.